Hi, I'm Eric, and I'm here to present Efficient Geometry-Aware 3D Generative Adversarial Networks, a general-purpose 3D GAN that is capable of high-quality synthesis, is trained from easily obtainable unstructured image collections, can generate convincing geometry despite not requiring any 3D ground truth, and is efficient enough to operate in real time. Many of you will be familiar with the basics of GANs. In a GAN, we have two models: a generator, which takes in random noise and produces a fake image, and a discriminator, which classifies images as real or fake. Feedback from the discriminator guides the generator to producing more realistic images. Now, taking a closer look at the generator, typically we use a convolutional neural network to predict the image directly. Here's the modification to turn this into a 3D generator. We break image generation into two steps. We first condition an implicit 3D scene representation. Then we render the scene representation from a random pose to produce an image. So this self-contained generator is almost a drop-in replacement for the 2D GAN. It takes in noise, and it produces a fake image. The difference is that at inference, we now have control of the rendering pose, and we can render the 3D scene from any direction we wish. But here's the problem. Neural rendering, in the way that it's typically done, is very slow. To render an image with NeRF volume rendering, we trace a ray for every pixel, and for every ray, we take about 100 samples. For each sample, we compute density and color with a large MLP. But these add up. 100 samples per ray, times the height and times the width of the image, suddenly we're dealing with millions of samples per image, each of which is computed by a large MLP. Not only does this limit the inference frame rate, but we need to render millions of images just during training. To put things into perspective, training a NeRF on a single scene requires about 4,000 renderings worth of compute. Meanwhile, the training of a single state-of-the-art GAN requires generating millions of fake images. And that's why efficiency is so important for a 3D GAN. Not only do we get better inference speed, we get faster training, we get higher resolution training, and the higher resolution training leads to higher image quality. So here's the central idea to a faster architecture. Instead of computing every sample individually with a large MLP, we first generate explicit features along 3 orthogonal planes. These feature planes span the volume, and an intuitive way of thinking about them is that these are like feature cross-sections. In architectural speak, if you are modeling a house, these might be your floor plan and section or elevation drawings. These triplane features can be computed in a single pass with an off-the-shelf CNN. Then, for every sample, every position in 3D space, we project onto the planes, we extract features, and we decode them with a really small MLP. So the main idea here is that instead of handling every sample independently, we do some prep work in creating these triplanes. But that prep work pays off because once we have these triplane features, we can compute every sample at a fraction of the cost. Rather than independently computing each sample, we front-load and share most of the computation. This more efficient architecture gives us a better inference speed, about a 35-fold increase in frame rate, but just as key, enables higher training resolutions, which results in a leap in image quality. With these improvements, we're getting much better quality at a much lower compute cost. So much so that we demonstrate high-quality, multi-view consistent generation and rendering in real time. Yet, unconditional generation is just scratching the surface. Future work may examine using the prior learned by the 3D GAN for novel view synthesis and 3D reconstruction. And still others may look to the interpretable latent space to find success in 3D scene manipulation. Here, we've improved upon the state of the art in 3D GANs with a better architecture resulting in faster inference, faster training, higher resolution training, and ultimately better detail in both renderings and shapes. We hope that EG3D becomes a general-purpose 3D GAN that lays the foundation for work with 3D generative models in the future.